Hello everyone, today I'd like to start discussion about an essential question. If you look around, you will see multitudes, many matters surrounding you, and each matters have its different property, and those properties are utilized in different ways. And you will see there was a table, there was a chair. If you're sitting on the chair is now collapsing, and a lot of those what we call the physical forms, we call the solids, liquids, and gas. And you may start wondering what actually holds stuffs together. So here's the essential question for this unit, and now we are going to explore the different interactions that are responsible for the properties you have observed or you start to observe in the lab. So the first part, we're going to take a look at ionic bonds. It's actually the interaction between ions. As we have learned before, and you should be very familiar with, and it's encompassed in the previous units we've been spending past several months in studying, and this is the key periodic table. You will see those are the groups or families, and the vertical columns, and you have the horizontal rows is called periods, and most importantly the electron configurations go hand in hand with the chemical properties. As we know, this group 1 elements will have NS1 valence electron configuration. The group 2 will have NS2, and group 16 will have NS2 NP4. Group 17 will have NS2 NP5. So it's total 7 valence electrons for group 17 elements, 6 valence electrons for group 16, and the list goes on. Most importantly, the noble gas electron configurations are deemed to be the most stable because they are chemically the most inert elements on the periodic table. Hence the octet rule. All the other elements wants to achieve noble gas electron configurations. For those alkaline for the metals on the left side of the periodic table, the easiest way to achieve the noble gas or stable electron configuration is by losing electrons. And on the right side of the periodic table, that will be the nonmetals, and the main mode to achieve the noble gas electron configuration will be gaining electrons. If you're losing the electron, you'll form positively charged ion because the number of protons from the atom does not change. But if you start losing electrons, more and more of the protons, they're going to be balanced out. So hence the overall entity will assume a positive charge. The reverse will be gaining the electrons. Those gaining electrons will not have protons to offset the negative charge on those electrons. Hence, or if the atoms gain electrons, you will result in negatively charged ion. You will be negatively charged ion. So here is the formation of ions. The driving force is the octet rule. So one of the very classic example you will see all the time is when we put sodium together with chlorine gas. This one will be metal, it will be solid. Chlorine gas will be represented by the G in parentheses, the S and the G in parentheses. Slowly you're going to get exposed to this. Is for the states of matter. This chlorine gas is going to be dissociated into two chlorine atoms. So you'll have the chlorine atom and the chlorine atom. Now you have a sodium atom and a chlorine atom. If you take a look at the ground state electron configuration for sodium, it's shown right here. You have 3 rings and two electrons in the first ring, 8 electrons in the second ring, and the last ring you have this valence electrons, you only have 1. On the other hand, chlorine atom, you will have also 3 rings, and it will be 2, 8, and 7. Interestingly enough, if you compare the size, remember how you compared atomic radius, effect number 1, effect number 2, effect number 3, recall that effect number 1 is number of rings. Here we do not have effect number 1 for neutral atoms, and we do have effect number 2 because chlorine has more protons than sodium. This one has 11, that one has 17. We do have 3, the valence electron effect, number of valence electron effect. Chlorine has 1 more, it should be slightly bigger. However, the 2 dominates. So here comes the comparison for sodium atom is actually significantly bigger than the chlorine. As we said before, the octet rule will dictate sodium would love to lose this valence electrons to becoming 8, as it has 8 underneath. And now chlorine would love to gain this electron, so becoming also 8 on the valence shell. However, when you draw this out, now the sodium ion only has 2 rings now, 2 and 8 electrons on respective principal energy levels, and chlorine ion now has 3 principal energy levels, which the last one also has 8. Now you will see the effect number 1 is there, effect number 2 is there, but effect number 3 is not there, but the effect number 1 dominates, and the order of size is precisely switched. Sodium ion now is much smaller than the chloride ion. Sodium ion is much smaller than the chloride ion. But one thing is shown around here, it's kind of a little bit misleading on those circular plots. It's sort of indicating all those electrons are moving on those principal energy levels is actually on a two-dimensional sheet, and as indicated by here. But however, those atoms, those shells are actually 3-dimensional. You'll be illustrated on those by these two graphs. It's actually, if you're looking in a correct fashion, and this is like a perfectly sphere. This is like a melon, and if you cut into it, this is the atom. This is actually the atom. You have a nucleus sitting in the middle, and now you have all those shells, or principal energy levels. And now the meaning of it is actually like an eggshell. It's a 3-dimensional. It's 3-dimensional for the inner shell of n equals 1. So you only have 2 maximum number of electrons on it. So then you go out. The second you have 8. The third you have 18. Fourth you have 32, and the list goes on and on and on. Okay, so the second one is also give you a good sense of that. You can see all those shells, what we call a 3-dimensional. This is the nucleus, and the electrons are floating on those 3-dimensional shells, 3-dimensional regions, and not as compared to the 2-dimensional as indicated on the circular plot. So now we'll have an interesting exploration on that. As we said it before, sodium, it will have a +11, and now you have sodium plus, and now we have 2 on here and 8 on here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8 electrons in here. But the overall will carry a plus charge, And now you start to imagine this is actually a ball. If I can draw it, use some shading, and the whole ball carries a +1 charge. Because all those electrons are moving very, very, very fast, surrounding the nucleus, and the nucleus sitting in the +11, and the 10 electrons could be anywhere at any place. So in essence, the positive charge on this sodium ion could be here, or could be here, could be here, could be here, could be here at any moment. So in essence, this whole ball over time, a short period of time, you're going to have average. It's all the positive charge. The positive charge is evenly distributed on the surface of this ball. Similarly, you will have the negative charge. In this case, will be chlorine. 2, 3. Okay, let's keep it consistent. Just erase this. Use the red one. This one, I actually use a green one. Plus 17. 1, 2, 3. Oops. And just wish I can have a little bit better control. 1, 2, 1, 2, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. So in this case, you have a negative charge on it. You have a negative charge on it. Same argument. This I'll use consistently. Use the green one, and you should have a negative charge on that. And this much bigger green one should have the negative charge evenly distributed on the surface of the sphere. So what would be the consequence for that? And this one we will see you'll have a fairly interesting, significant consequence for that, which means let's just simply draw it. And if I have a sodium ion in here, if I draw it right on this corner, it really doesn't matter where the chloride ion is going to be located, right? If I'm going to say chloride ion is going to be located right here, here will be the interaction, right? And your chloride, if I draw it over here, it will be the interaction. If I draw the chloride here, and it will be the interaction. If I draw the chloride here, that will be an interaction, because remember all the charges are evenly distributed on the surface. So whenever you put those chloride, and you have the same interaction with the sodium ion. So it's a key conclusion. Let's see. Ionic bonds, the interaction between the positive and the negative charged ion are what we call non-directional. It's any direction you'll have the same interaction as long as you keep the distance the same. So the important concept is demonstrated. But what was the consequence for that? What was the consequence for that? That will be the consequence is you have the positive charged sodium ion. You will be surrounded by negatively charged chloride ion, because it's non-directional. So any surface of positive and negative, they can attract to each other. And remember, the attraction is what we call the electrostatic attractions. Electrostatic attractions. This is one of the 4 fundamental forces that governs the universe, and it's a fairly strong one. And now you can see they can now actually pack the chloride ion, and between chloride ion will be sandwiched by the sodium ion. Okay, so this is actually is going to be packed into what we call a regular array, a regular arrangement, because it repeats itself. It's the negative plus, negative plus, negative plus, and you can go on now. Those are called, and you're going to see it's crystals. And we're going to explore more later. So what I want you to actually show you one good is actually, I want you to look at the sodium chloride, an example of the ionic compound. In this case, I'm going to put up on the slideshow. So as you can see, sodium chloride, you have one big ball, a big sphere. It's the chloride ion, and the smaller one will be the sodium ion, but does not exist as a single unit, like in water molecule H2O. H2O is a water molecule. It stands for, each molecule of water has 2 hydrogen atoms and 1 oxygen atom. But for sodium chloride, it doesn't apply. Why? Because they're all packed in solid as a crystal. You have pluses, you have minuses, you have pluses, you have minuses. This is the good, or we call the lattice representation of sodium chloride crystals. Sodium chloride crystals. As you can see, you can actually, this is a 3-dimensional image. You can turn it around, and you will see the yellow. The yellow represents the sodium ion, and the big, a little bit orange yellow ones will represent the chloride ion. It's all sandwiched in between. It has a very, very regular packing order. We call it the lattice. So formula unit for sodium chloride is an ACl, and if we look inside the crystal, each of the sodium plus and chloride ion are bounded by 6 oppositely charged neighbors. So let's shrink the ion so we can actually take a peek inside. Just shrink it to take a peek inside. So you can take a look at this. It's very nice. So actually you can rotate, and let's take a look at the chloride ion. You can take a look at the chloride ion, this one, and you will be how many sodium ions close enough to bond with, and you actually can start count them. Again, from the head-on view, and you can take a look at it. Now you can start looking at it. Those are the ones. Those are the ones. You can turn around. You can actually, for each chloride ion, you can have 1, 2, 3, 4, 5, and 6. Okay, so 1, 2, 3, 4, 5, and 6, and 6 sodium ions you actually can bond it with. And how many chloride ion? If you're looking at the reverse, each sodium ion is bonded to. So now you can looking at the sodium ion is bonded to 1, 2, 3, 4, 5, 6. It's a 6 of them. 1, 2, 3, 4, 5, 6. Any place you're looking at it is 6 with 6. Okay, so it's a 6 with 6. So each sodium ion is bonded to more than 1 chloride ion, and each chloride ion is bonded to more than 1 sodium ion. Then all the ions of the whole crystal are part one single bonded unit. And this whole thing represented here, this drawing will be sodium 32 and a chloride 32. Okay, so it will be sodium 32 or chloride 32. But that's kind of impractical if you have all this ions drawn, and you'll be really cumbersome to write. So if only the ratio of ion is given, and this is actually called empirical formula. This is what we call a formula unit for ionic compound. It's not the molecule, it's actually the formula unit. It's the simplest whole number ratio between ions. For in this case, sodium chloride is the formula unit for the sodium chloride crystal. And sodium chloride, smallest whole number ratio of sodium and chloride ions in the crystal. So with that, and we are going to switch back, talking more about the ionic compounds. Interestingly, as you have done in your lab, you started observing the properties and certain properties associated with ionic compounds. The compounds are formed between the attraction of positively charged cations and negatively charged anions. In general, those are the ones you've done with the table salt, you've done with the Epsom salt, you've done with alum salt. So it's usually doing a dull in appearance. They're usually kind of a whitish looking color. If you really grow the crystal, it will be clear. Big single crystal will be clear. And they're all pretty hard. But if you push hard enough, they actually exhibit brittle behavior, because if you can put enough pressure on it, it actually shatters. And if you check on the physical properties, they are fairly high in melting and boiling temperatures. And when you measure the conductivity of the solid salt, the pure form of the salt, they don't. There's no electricity going through it. But however, we didn't do this. You didn't do this in the lab, but it's been done on an industrial scale. When you melted the molten sodium chloride, the molten table salt conducts electricity extremely well. They do conduct electricity in the molten form, and most, but not all, it's readily soluble in water. And whenever they dissolve in water, it becomes a homogeneous mixture. We call it aqueous solution. Aqueous solution of the salts conducts electricity well. They do conduct electricity. So you have these observations regarding what I generally call them macroscopically observable properties. You know, the appearance, the brittle, the hard. You can measure the melting point and the boiling point readily. You can actually measure the conductivity readily. How is that related to the microstructure, as we shown here with the crystalline lattice structure, and also this alternating sodium plus ion and chloride minus ion. So as we can see here, for the property of hard and high melting temperature and boiling melting point and boiling point, it's all because of the very strong interaction between the sodium plus and the bigger one, the chloride minus. The interaction between those is very strong attraction called electrostatic attraction. So when you're trying to pull them apart, that's what you do, trying to break them, it will resist. So it's hard. And also when you're trying to melt them, also kind of pull them apart and melt them or boil them, it's you have to overcome this very strong attraction. So in essence, this strong electrostatic attraction makes it hard, makes it a high boiling point and high melting point. And the other thing to look at it is the chloride ion is charged, the sodium ion is charged. Both of those can actually carry electricity. However, in this lattice structure, those ions are locked in space. So they are fixed. They cannot really move around. So in the solid, pure form, the ionic compounds do not conduct electricity. However, when the whole lattice structure is destroyed, when it's being melted, so in the molten form, all the ions are freed up. Ions are freed, so ready to move around. So it's a good conductor of electricity. Okay, so then what would happen with the other property, what was called why it's brittle? Why it's brittle? I want to show you another sequence. Some other folks put it together. I thought it's very, very useful to understand that. So this is a kind of two-dimensional. Let's choose a color so that I can actually really show it here. Best it will be the white. So this is actually a two-dimensional representation of the lattice structure. So we just projected onto this piece of black paper. You have the plus, you have the minus, plus, minus, plus, minus, and my apology in this. It's kind of drawn a little bit off scale. In this case, the big one should be the minus, and for our case, for the sodium chloride. But you can find some other combinations of cation, anion. This is actually the case. But the other side, there's a little detail. Okay, so this is a plus, minus, and it's have to be surrounded by the minus, plus, minus, plus, minus, plus. So this is a perfectly aligned lattice structure. Perfectly aligned lattice structure. In this case, I also need to put on a slideshow. So as we fill this lattice structure, if we apply a deformation force, if I really push it hard, initially it's going to be hard to move because the structure, because the attraction between the positive and the negative is very strong. But if we can actually manage to move it just a slightly bit, just move like an ions diameter of ions, and now you start to see the problem. Instead of positive negative, now I have positive negative negative, positive positive negative negative, positive. Those are same charged ions. What will be the interaction between those? They are not going to like each other. So what they're trying to do, they're going to repel, and in this case, and it's going to fracture the crystal. It's going to fracture the crystal. Okay? It's going to fracture the crystal. And I would really like to kind of replay. Let's do a replay. So when you have a very strong ionic compound crystal, so you have this perfect arrangement, plus, minus, because of the strong interaction, electrostatic interaction between the plus and minus is hold it up very well. It is very hard. It's very hard to move them. However, if you manage just to move them a little bit, a slight distance, is only about an ion's diameter, then we're facing a problem. Instead of the opposite, instead of ions with opposite charge aligned to each other, now the ions with the same charge aligned with each other. So then they repel each other, and it causes it to fracture rapidly. It's caused it to fracture rapidly. So let's get out here, and so then this ionic crystals cleave because the like charge of shifted ions repel each other. The cleavage often results in a sheer, smooth face between the split crystals. Okay. So let's switch back. So we actually explained why they're brittle, and the other one is the solubility, soluble in water. And as you probably already done so in your own kitchen, you put the salt in the water, you will see the salt disappear. And I want to show you a YouTube video actually under the microscope. It's pretty cool. So if I can get this one started, okay, you will see this is just a table salt, and put it under the microscope, magnified about 100 times, and you can see this is got a very regular shape. The reason why they have the regular shape, remember, they have the crystalline lattice structure. They organize it very, very nicely. So now the water came in, and you can see they quickly disappeared. Look at how fast it goes, and it's just gone. It's just gone within 10 seconds. Within 10 seconds. All right, let's take a look at what the others. This is a much bigger piece. This is a much bigger piece, and the water is going to come in, and now start seeing what actually happens. And let's try to find it. And let's try to find it. And we're still looking. We're still looking. Here we go. So this is the one is under the water. Is under the water. Okay. So that's the edge of it. And now you can actually start seeing it to disappear. Seeing the salt crystals to disappear. Seeing the salt crystals to disappear. And you can see how fast it moves. And that is quite astonishing. Now you see the nice, well-packed salt crystals literally disappearing under your eyes, and is totally dissolved into this water aqueous solution. Okay. So in a very short period of time, and this whole salt crystal will disappear. And this probably make you start wondering, what is actually happened? What is actually happened to the salt crystal? What is actually happened to the salt crystal? Okay. So with that in mind, I actually want to show you kind of animation to answer those questions.
Let's add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water. Click on the zoom button to view sodium chloride dissolving in water on a microscopic scale. Polar water molecules interact with the positive and negative ions of a salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between water and the salt ions causes a salt to break apart or dissolve in water.
It's a very interesting animation, and you can see this is the lattice structure, and now the salt crystals is being destroyed by the water molecules, literally picking apart the ions one at a time, because there's so many water molecules around. The process is actually pretty fast. But very interestingly, you can see those ions being surrounded by water and they've been pulled into the solution. Now they can be free to move around, and they can carry the electricity. So hence it's readily soluble. A lot of the salt is readily soluble in water, and as soon as they become soluble in water, make an aqueous solution, they conduct electricity. So here is what is a very important concept, is the properties of ionic compounds is determined by the microstructure, by this ionic microstructure, the crystalline structure, and also the positive and negative charged ion interactions. The other one is why it's dull in appearance, because there's no free electrons. They're all ions, perfectly happy with the octet, with 8 valence electrons in this case, for both the sodium ion and the chloride ion. The hard, as we said before, is due to the strong electromagnetic, sometimes referred to as electrostatic attraction. It is brittle is due to the crystalline structure and the repulsions between ions of the same charge. So if you have the positive and then are lined up just by slight deformation, then they will fracture. It's high in melting point and boiling temperatures. It's also strong electromagnetic attraction. They do not conduct electricity in solid form. They're all locked up. The ions, the charged particles, they all locked up. But if you destroy the lattice, if you let the ions free to move around, conducts electricity very, very well. Most but not all, remember we're going to talk about that in the later units, readily soluble in water. It's because of the polarity of the water can literally pluck those ions from the lattice structure, dissolve them into aqueous solutions. And now if you are in the aqueous solutions, and those do conduct electricity, but those charged particles called ions are capable of carrying electricity. So this is the one, is a very, very important concept. So I will emphasize it once more, is what macroscopically we observed phenomena, like the appearance, like how hard, it's brittle, high in melting and boiling temperatures, and whether it conducts electricity or not conduct electricity. Those are all determined by the scale, the microstructure on the scale of ions, the tiny, tiny scale. And in terms of how we're going to call those ionic compounds, it's called a nomenclature. This will be addressed in a separate vodcast. So that's pretty much it for this vodcast. Thank you very much for your attention.